With that, I'm going to turn it over to Randy. Take it away.
Awesome. Thank you, Jeremy. As Jeremy mentioned, I kind of want to talk to you about some of the research we've been doing about, as it says on the title there, doing more with less. And in particular, research we've been looking at to develop the decision support tools that states and other entities that have a network of assets to manage can use to find strategies that will allow them to keep the performance of those assets, the performance of those road networks high and at the lowest cost possible. So I think that most of the folks on the phone know why we would be interested in this topic of how do we do more with less, but just to bring it home maybe a little quantitatively, I kind of thought there were 2 or 3 points that really strongly motivate why we've been working in this space. I mean, the first of one is that one that probably everyone experiences in one way or another every day, or at least every week, which is that within the U.S. for quite some time, we've not really been sufficiently investing in our road system. Most of you are probably familiar with the fact that the American Society of Civil Engineers comes out every few years with their report card on various aspects of infrastructure within the U.S. And the last one that has been made public is from 2017, and our road network got a grade of D. In fact, what their report card showed was that actually 21% of U.S. highways are actually in poor condition. And not only that, but so as a result of that, the fact that there are so many in that state, there's over $1 trillion gap in their estimate in terms of what would need to be spent in order to keep up with and address those needs. So that's one part of the problem, is that our system is in a state that's not where we would want it to be. The other part is that our infrastructure spending is not actually going up. As a matter of fact, at least as of 2017, total spending on infrastructure was at sort of the lowest rate it had been in about 2 to 3 decades as a fraction of overall GDP. You can see the plot here on the left from the New York Times, basically showing that we're spending about almost a third less as a fraction of GDP in 2017 compared to where we were in 1993. So together, basically, these clearly point to a problem that we're behind on that spending, and we certainly don't seem to be on a slope to make it better. So fortunately, the ASCE report card doesn't just sort of point a finger and say that things are bad, but rather also include in that a number of solutions that they feel would be important to kind of change the state of the game, so to speak. Obviously, one part of it is to increase overall funding through changes in some of the key mechanisms like fuel tax and other things. Once as funding is there, to basically spend that to address some of these backlog of rehabilitation needs. But the point that we're here to talk about today is actually the third point, which is essentially to make sure that best practice is followed in order to put those dollars, whatever that set of dollars is, to its best use. To take the dollars and make sure that we are driving toward a system that is meeting some level of performance target. And so of these 3 important solutions, one of them is this charge to use asset management best practices. And that statement there is really one of the key motivators for why we have been pursuing this topic within the hub. The other thing, just to be made aware of, to kind of, that's not just ASCE that's making this claim. FHWA has also issued guidance and rules about how to drive performance management within the system through the MAP 21 legislation. And in particular, they note the need to improve decision-making through what they call performance-based planning and programming. And to key elements, one aspect of that is for states and other asset holders to develop what they call asset management plans. And those involve a number of different things, including life cycle planning, risk management. But when you look into the details of it, the topic that they call performance-based planning and programming is ultimately, and I'll try and make this point a couple of times, a key element of that is the asset management decision tools like what we're going to be talking about today. So when you look at both what FHWA has laid out and the way that individual states and municipalities are developing these asset management plans, you kind of see a very common thread across them as involving three major tasks that have to be addressed. One is that the manager of the system, the holder of the assets, needs to actually set planning or performance targets. It's very commonly done to set those around the percent of assets that are in a good state, the percent of assets that are in a poor state. There are other metrics that one can choose, and obviously there's some kind of measurement system that has to sit underneath that in order to determine good or poor. In addition to setting those kind of targets, it's important in order to have a sort of valid asset management plan, one needs to obviously measure that performance. It's not kind of a rocket science revelation there, but there has to be some system in place to understand what that performance is today and some recurring system to continue to manage that. And then finally, once you know where you want to go, the target, once you know where you are and how to measure what your state is, the state of performance is, then the other key pillar is to develop some strategies to get from where you are to where you want to be. And that one of the key aspects of that strategy, well, that strategy, if you think about it, involves a few key questions. What are the actual treatments or other activities that will occur to change the state of the system? We'll typically refer to these as preservation, rehabilitation, and reconstruction strategies. You need to know something about both their cost and then the budget that's available to undertake those strategies. And then ultimately, and the question that we're really targeting today is how would you allocate those funds across those strategies to actually meet your targets at the lowest cost? The reason that seems like a fairly simple question, but the reason it becomes really challenging is because of the fact that, in point of fact, there are many different approaches that one could take to allocate those funds. So this is just sort of a kind of a trivial little example here. Imagine that you had a network that comprised 7 different roads, pavement segments, we've listed them here. They're all in some different level of condition as measured here by a sort of arbitrary index, pavement condition index. They all have different levels of traffic volume associated with them. And the question that you're confronted with is, which of these segments would you repair first? What targets what levels of performance, pavement condition index, will you attempt to repair them to? And then which types of treatment technologies would you apply to undertake that repair? Would you apply short-term options, longer-term options? And you can imagine, just looking through the list there are lots of different strategies, even just for the prioritization question, which is, would I go after the worst pavements first, even though in this example they're not the highest traveled segments? Would I focus on the medium level segments like segment D, which is sort of at a medium level of performance but a very high level of traffic volume? What is the right way to allocate that? And even in this case, we haven't even added to the example the fact that there would be different costs of addressing these levels of performance. So you can imagine that the problem can get fairly large fairly quickly. And the only way to do this in a consistent way that balances all of these different issues is through some quantitative modeling approach and what we're calling an optimization model. And as I mentioned earlier, this is a thing that has been identified within by the FHWA as a key element of what they refer to as performance-based planning and programming. So the way that we have been approaching this problem from a general perspective here is to think about there being three key pillars of realizing a truly effective asset management support system or a performance-based planning system that would allow for effective budget allocation. And sort of the three key pillars of that match up very much with the way that I was talking about the pillars of the asset management plan earlier. One is understanding the current and historical performance of the network that you're trying to manage. Using that data then to develop models that will allow us to project how the performance of the network would evolve over time, both in a case where we don't do anything to that network, but also equally importantly for the cases where we impose some kind of treatments of various types, whether those are just surface refinishing type treatments or all the way to full reconstructions. Another aspect that kind of runs along in parallel here is that an important part of that current and historical pavement data is not just the performance of the system, but also the costs of undertaking various treatment options. So we also feel it's really important to be able to have reasonable projections of how those costs will evolve over time. But once we have that understanding of where we are, we have those models of how network performance and costs would evolve over time, then we need some algorithm that's going to pull all that together to help make effective decisions about how we would allocate those resources to their most effective end use, to how we would prioritize the projects that are going to maximize performance, but at the same time manage or minimize cost. One of the things that I think that a lot of folks just don't have a good appreciation for around this topic is just what the actual scale of the decision problem really can be. And so, one way that I thought about it is, a state is confronted with a decision about, which activities do they undertake, so preservation, rehabilitation, or reconstruction. Which of those activities do they apply to which road segment, and then at what point in time do I apply that activity now, or do I wait to do it in a few years out in the future? And it's the combination of all these different options for a network of the scale that most states deal with that make it very difficult to try to do this without some kind of computer tool. And just as kind of an example, I pulled some statistics from the state of California, recent statistics. So if you think about, they have 50,000 lane miles of pavements. So maybe that doesn't translate into 50,000 segments, but it certainly translates into thousands and thousands of pavement segments. Within their asset management plan, they talk about more than 50 different options of how they could do preservation, rehabilitation, or reconstruction on those thousands of segments. And then they have billions of dollars which have to somehow be allocated across those. And all of that time looking out at an uncertain future about how the road condition would evolve and maybe even what their budget would be in future years. So it leaves a really big question, like what is the best plan on how to deal with a situation like this? So one way that most practitioners, including ourselves here at MIT, have tried to grapple with the scale of this problem is to sort of break it up into two different aspects of the problem. And this has really been a promising strategy for us in terms of one of our real analytical goals, which is how to address that uncertainty that I just kind of implied in the previous slide. And so the two interlinked tasks are if you think that there's a network overall that needs to be managed, but that network comprises many, possibly thousands and thousands of individual pavement segments. And so we can think of this, we can approximate our best decision by thinking about the question of what are the best things that can be done for a given segment, given its current state, and what different treatment activities are available to apply to that segment. And then once I've identified maybe the best or the best and second best, second and third best options for a given segment, which of those should I choose overall for the network at a given point in time in order to get the best performance out of my network, but to still stay within the budget that I have available to me? That's my budget allocation problem. You know, just to give you, maybe just to make this slightly more concrete, if you will. So if we have some road network here in eastern Massachusetts, that road network is broken up into many different little segments. So those little chunks between the dashed lines are intended to represent segments within the network. And each of those segments, I might go through and identify what the best maintenance, rehabilitation, and reconstruction options there are. So maybe for the first segment, my best option would be this year to apply some short-term maintenance strategy, and then in a few years do a rehab strategy. For the next segment, there may be, sorry, animation here is not cooperating. There may be another set of activities that are best for that segment, and I go through my entire network. Then, once I have identified what those best options are, my next question is, which of all of these options am I going to be able to apply in a given year, and which set represents the best set to apply in a given year in order to meet my targets in the long run, my performance targets in the long run. And so that kind of breaks the problem down, as I've shown here on the right-hand side. So we understand where the network is. We understand our best decisions for each segment within the system. And there are a lot of different analytical approaches for making that decision. Currently, most states rely on expert judgment. Many states that are in kind of the process of executing their asset management plans are moving to models like what we're talking about today. The majority, or all of the existing models that we're aware of on the market today, don't consider uncertainty. That's a topic that I'm going to emphasize a lot as we move to talking about our specific approach. And then obviously, as I'll talk about starting in the next few slides, one can also consider that uncertainty in a probabilistic model. And then once I've identified those best strategies at the segment level, there are a number of different methodological choices that are available on how to look at the allocation problem overall, how to choose the best set for your particular goals given your particular budget. Key differences in the way that, as I mentioned, there are models and approaches that are on the market for states to use, and there are a number of states that do use those types of models. So what we've been trying to do is sort of move the performance level of those models themselves in order to, as you'll see, hopefully allow states to make even better decisions than they do today if they already use one of those, or just to move to this kind of model immediately. A few summary issues that kind of highlight some of the key differences between the approaches that we have taken compared to what you see on most of those models in the market. I've sort of highlighted three areas here. One is that we have tried to create a model that's able to look at much longer analysis periods than many of the models out on the market today. And that obviously probably doesn't take much to realize that looking at farther out into the future creates a lot of computational challenges because we're looking at more and more events that can happen out into the future. But part of the reason that we think this is an important thing to do is because whatever decisions we make about how to maintain, or preserve a road today influence what we would do with that road out in the future. And so if I'm only looking at a 5 to 10 year time horizon, I can only capture a small amount of those future consequences. And so without a model that can look far enough out, we're not able to fully capture, fully understand, or fully represent what the consequences of any given decision today is. The second thing that we have been trying to do within the model we're developing here at MIT is to move away from predetermined decision rules for a limited number of maintenance or preservation, rehabilitation, and reconstruction alternatives. What I mean by our prescriptive or predetermined rules are ones that are based on conditions that exist in the market today. And what we know from looking at historical data is that the conditions of future markets can be very different from what they are today. One material may be more expensive, another material may be cheaper than it is today, or vice versa. And so if we set up a model that works off of a predetermined set of rules, chances are we're not going to be best positioned to deal with those future uncertainties. And so we've been trying to build in what we call dynamic decision rules. And that obviously adds some computational challenge, but we've still been pushing ourselves to do that for an even larger set of alternatives. And you'll kind of see why that's particularly important. Now, one of the consequences of looking out further, trying to build a model that's going to look further out into the future, is that necessarily the future is uncertain, and the further out that we go, there are more uncertainties. There are more uncertainties about how a network's performance will evolve over time. There are uncertainties about what the prices and costs will be for any given, for treatments that are used within that system. And so another big goal of ours that is in part motivated by the first two is to create a tool that is explicitly considering that future uncertainty and factoring that into the decisions that we make about treatments today. One of the things I didn't highlight as much earlier, but some of the guidance that comes out of the MAP 21 legislation also encourages states to shift to a decision-making perspective that considers future risk. And you really can't do that unless you're looking at this future uncertainty. So we feel like that's another important benefit of this shift in approach. So one of the ways that we've been trying to build in the ability to consider uncertainty into these kind of tools is through the use of what an approach called simulation optimization. So if I take a step back, you can kind of imagine that one of the real challenges of considering uncertainty in any kind of problem is that the scale of the decision problem becomes much larger. So if before I had thousands of segments and I had dozens of different technologies, now I have to think, well, what's the best one if the future develops like future A as opposed to future B as opposed to future C? So it's understandable that this issue hasn't seen wide deployment to date, but basically through the advancement of computer power, we can begin to bring that kind of information into effective asset management decisions. And the way that simulation optimization works is kind of just written in the name there. We still at the core have an optimization model that is going to apply mathematical algorithms to try to find the best use of funds to meet some particular performance objective. But we're going to take that optimization model and apply it into hundreds, if not thousands, of different possible features for each segment within the system. And so when we talk about different features, we mean maybe there are different weather conditions or different traffic conditions that lead that segment to deteriorate faster or slower than we might typically think that it would. Maybe there are economic conditions that push the key factor prices for various treatment alternatives higher or lower. So there are many different possible contextual variables that can change within those features. But we use simulation to project different features, and then we use the optimization model to plan a best strategy for that. Once we see the characteristics of all those different plans across all those different features, then we can actually pick among them for plans that are basically balanced. What's our lowest cost option versus our most risk robust type option? And different decision makers will make different trade-offs there. You may be very risk averse, and so you might spend a bit more but get an option that puts you in a much lower risk position for the long run, or you may choose the opposite. The plot that I have over here at the right is really just to be a little bit indicative of the ramifications of considering this future uncertainty. And so it's a bit of a tricky plot, and I apologize. Anytime we bring uncertainty into the picture, it seems to make it difficult to kind of communicate the results here. But what this is a result of is sort of a partial result of this simulation that we were talking about. I was talking about just a moment ago. And so we're looking at one particular segment, and what these curves represent is the distribution of the cost of maintaining that segment over a 20-year time horizon. And so the large dashed line here is intended to represent decisions that are based on a conventional approach. So a conventional approach, what we mean by, is not considering uncertainty in the initial decisions. And you can see that when we make that decision not thinking about that future uncertainty, we end up putting in places that aren't able to, putting in place plans that are not able to respond to poor conditions or better conditions as time evolves, and we end up with an overall higher cost. You can see further to the right, higher cost option or understanding of how the cost of maintaining that segment would be. Now, when we actually plan based on what those what we know about those possible futures, we can have the model make much better decisions about how it would manage that segment over time, and in fact, what decisions it would make about that segment today. And so we have just a couple of different versions of how much we allow the model both to simulate and how much we allow the model to make decisions about that segment, as opposed to making all the decisions today. The main thing to take away from this is basically just to see that when we fully consider what that future uncertainty is, we can end up with a very different understanding of what the cost of managing that particular segment would be out into the future. And so if we're wrong about what the cost is, like what we would say this heavily dashed line is, we're obviously likely to make incorrect decisions today compared to what the optimal decision is. And so that's what I hope that this figure might begin to show, is that when we consider those simulated features, we can get a very different understanding of what the distribution of costs would actually be compared to what we might think they would be. And so hopefully by getting that better understanding, we can make better decisions. And so just as an example, this is a limited recent case study that we've been doing of the Iowa State Interstate Network. And so maybe focus first on this plot in the lower left-hand corner, where what we're looking at is the same network that is being managed using two different decision approach methods. The gray and black line approach being what we would kind of call a more conventional model that is based off of not considering certainty, so it's a certain future-based model. And then our current modeling approach, which tries to use this simulation optimization method to factor in that uncertain future and then therefore make better decisions today. and you can see these are both managed under the same budget level. And yet, when we think about that future uncertainty, we can make plans that put ourselves into a much better position in the long haul. We want higher pavement condition index is sort of the goal in this. And so, how does that uncertainty-informed model do a better job, so to speak? And the reason it does a better job is it deploys more longer-term solutions early in the planning horizon, which therefore puts the system into a better place in the long run. And you can kind of see that by comparing these two figures in the middle figure and the far right figure. The uncertainty model is the sort of distribution of different technologies that is being applied by the uncertainty model, and you can see longer-term solutions having a bigger position within the overall portfolio, and that puts the system in a better place. So I just show this as a bit of an example, but more importantly, by applying these kind of models, we have begun to learn some common lessons that I think would be applicable to many systems. And these have been built out in a more extensive case study of the North Carolina interstate system, and so I just want to share with you some of those results really quickly, and then we'll wrap up. So the modeling I'm going to show you is based on this the same approach I was just talking through. So we've collected up data, we've built up models of how performance and cost would evolve in that system, and then we've applied these models to make these allocation decisions. And so what we want to do is see how performance changes under different conditions. And from that, we basically have kind of pulled out what we think are 4 key learnings about these types of systems and how to manage them better. And these 4 key lessons are the importance of mixes of pavement types, the mixes of long-term and short-term fixes, to have long planning horizons, and the 4th one's probably something that anyone could have figured out, which is that you need to have enough funds to do the job properly, but nonetheless, we can do it fairly quantitatively. So just to walk through, how do we reach those conclusions? So the way you want to look at this plot here, and I'll show you several of these, along the x-axis, we're looking at systems that are managed with increasing amounts of budget. And then on the y-axis, we're looking at the average, and if you wanted to look at the distribution, you can see the whiskers around any given point, but effectively the average condition of that system. So first off, shouldn't be surprising that we have a generally upward sloping curve, so as we have more budget, we have a better conditioned system. But what is really interesting about this result here is that the 3 different lines that we're showing are systems that are simulated within the model to be managed with either the red line is a system that has only one kind of pavement, in this case it's an asphalt pavement that's available for future use. The purple line is a system that's managed where only Portland cement is available for future use. And then the green line is a system that's managed where both kinds of materials are available. And the dashed horizontal line is intended to hopefully make a point about a really interesting conclusion that we see from this, and that is we could manage a system to the same level of performance, this dashed line here, using any of these 3 approaches. We could get to that level of performance with a system that only used asphalt, that only used concrete, or that used both. But notice that the system that uses both can be managed to that level of performance at a much lower cost. So that has been one of our key conclusions, and I think in interest of time, I zoomed in on that particular point there, but I think we've kind of seen how that point. But what I did want to emphasize is why would that be possible? Why would it be true that a diversified network could be managed to a better level of performance, but at a lower cost? And the reason is because that materials costs change over time. This is a story that I pulled from the local Decatur, Illinois paper from a couple months ago, just talking about how asphalt prices had changed, and therefore that had some ramification on how they could manage their own road network itself. And this isn't intended to say that this is an issue only with asphalt, but only to really just to point out that if you make your plan in 2017 and prices are different in 2019 when you're having to execute that plan, if you have a system that is only dependent on one material, you have very little ability to respond to that. If you have a system that comprises multiple materials, there is a higher likelihood that prices may not move together, and you have a more robust plan in the long run. So another similar point that we have noticed is that it's not only important to have a diversity of materials, but a diversity of technologies that you can apply. So what we're looking at here, similar kind of plot, simulating a network where the black line is only preservations technologies are available to manage the system. The yellow line is a system where only rehabilitation and reconstruction technologies are available, and the green line is one where both technologies are available, and similar kind of point we see. We can pretty much manage the system to this dashed line in any one of those approaches, but the system that has both is able to do that at lower cost. So important to have a mix of materials, important to have a mix of short-term and long-term fixes. And then finally, it's important to both have a long planning horizon and obviously a sufficient budget. So what we're looking at, if you focus on the plot here just on the left, same type of analysis, but looking at a system that's managed with only a 1-year planning horizon, a 5-year planning horizon, and a 20-year planning horizon. And we can see a very same type of lesson. When we look further out, we can make these better decisions and therefore manage a system to the same level for less. And the double benefit here is that not only is it, when we manage it to that higher level of performance, we also get lower emissions out of the system as a whole. So those are kind of our 4 key lessons and the 4 observations that we have noted. We think that some of the things that sort of derive from that states need to be building into their performance-based planning systems are, 1, to move towards tools that are going to allow them to analyze longer planning horizons. They need to develop out the set of cost and deterioration data that is going to give them good models that also include uncertainty about those future costs and deterioration. And they need to develop out the data and the capability to make sure that they have a diverse set of materials and preservation and rehabilitation, reconstruction alternatives available to them to manage their system. And one of the things, I think that's probably a good place to end right there, is that these are, from the lessons that we have learned, these are things that we think that states would benefit the most from focusing on. Those tools that allow the longer analysis, the tools and methods to capture cost and deterioration, data evolution over time, including uncertainty, and the capability to handle many different preservation and rehabilitation alternatives. So with that, I think I'm going to turn to Jeremy for questions that have popped up along the way.
Yeah. Thanks so much, Randy. That's extremely helpful, and you gave us a lot to consider. Just as I mentioned, if you do have questions that you'd like Randy to answer, please go ahead and type them into the box in the lower right. We already have some coming in, and so, but we'll be glad to talk about them in the remaining time that we have. All right, the first question is, your probabilistic optimization approach is very timely. Have you considered developing transitional matrices for various fixes and projecting future condition scenarios with funding allocation strategies as one would obtain in a Markov chain?
Yeah, so the simulation optimization approach does depend on kind of a Markov assumption. It is an interesting thought. I mean, I would I think that probably one of the things that motivates a question like that is that a Markov approach has proven to be a very scalable approach. One of our big challenges is that when we think about cost being also uncertain in the future, then the kind of best decision that occurs at any future point can be very different than what would be true today, even if all the other state variables are the same. And so there are a number of different strategies that we've been looking at. How do we continue to scale this approach so that we can go to even larger and larger problems? That's one of the ones that's on the table, but we appreciate it as a
There was a follow-up question that's pretty specific from the same person about whether you'd combine a Markov's chain with a Hungarian algorithm as an alternative approach.
Yeah, I don't. That's something I think we should look into, but I don't know that I have a specific answer right now.
Sure. Yeah. Another question that's on our website I can answer based on our website is, where can we find a paper or document about this research? We have a couple papers that are already on our website, which is cshub.mit.edu. And if you go there and click on the Pavements tab along the top, and then Network Asset Management, there's quite a bit of this work that was done. The topic summary that's listed at the top of that has some of the charts that Randy showed, and then there's some other peer-reviewed publications that are down there that get into some of the details on this as well. So, all right. While we wait for maybe some other questions, Randy, I think we've been talking quite a bit with DOTs about the current approaches that they use to performance-based planning. What do you think are some of the barriers or challenges to implementing some of the those 4 key recommendations that you mentioned?
Yeah. So one of them a little bit was what I could even actually show what was going to be the next slide here, just I was worried we were running out of time. But one pillar of all of this is having good data about the current system, but even more challenging is how that system would evolve over time, and those kind of models need to be particularly good the further out we're going to be looking into the future. And so one of the things that we've noticed as a challenge is just the quality of data that many states might have currently about their historic performance of their system. So what I'm showing here is the data that we got from a state that I won't name, but just so you know, this is actually one of the better data sets that we've gotten from a state. And what we were looking at were measured IRI values recorded by that state over a 12-year period. And the thing that's kind of interesting about this is that, and we've normalized them all to just an arbitrary 100 just so it was easier to compare them. But you can see many of these segments that at the end of the 12 years, even though they don't claim to have had any kind of treatment done to them, ending up with a lower IRI or lower roughness index than they started with. And so some of these may have treatments that actually happened but never got recorded. Some of this may represent data quality issues. So, one of the things, there's actually been an earlier public webinar about this that the Hub's trying to do is come up with some lower cost ways to collect this data. So that's one of the things is having good models. I think there's also kind of a perception issue that I think you probably may even be able to speak to better than myself, but that a lot of folks feel like that looking further out into the future, there's just too much uncertainty. How could we possibly learn anything from that? And so I think what we're trying to do is develop out enough case studies to sort of overcome that concern. I think it's a valid concern to say, hey, yeah, there is a lot of uncertainty, but even when you account for that uncertainty, you can actually do a better job. So.
Along the lines of all models are wrong, but some are useful. How do we make sure that that these are useful? So.
any other questions that have come through?
There haven't been. So for those who are interested in there's a chat window, which is a separate box from the Q&A that you may need to open, but I just included a link in there specifically to the part of our website where we have more research on this, on the asset management related work, and would be glad to follow up with any questions. I think, did you have a last slide on there that has our email or?
Yeah.
Yeah, that's our website as well, and then also if you have any questions or comments, you can reach us that way. In case you wanted to go back and listen to this or know someone who wanted to attend and missed it, we have a YouTube channel as well where we'll be posting this recording, so you can go back and listen, and we look forward to hearing from you and then having you join us also next month for our next public webinar. So thanks so much, everyone, and we'll talk to you next time.